are in the pre-design phase. And here also testing is necessary. Testing is necessary to look what the performance is of a device or a system, what the quality is. Quality means how it is in accordance with the specifications, mostly on a short-term basis, and reliability, which somehow describes quality over longer time in the use phase. Yeah. So for all of these aspects, testing is necessary, and here we have the phases: design and development, and production and supply. And before that, we also have a phase of research, and here also testing is necessary. Okay. Yes. Now let's go to the device level. So a device is a single part, like this battery, or let's say some component which is inside such a small system. So let's address individual devices. And we have already seen why such devices fail, and that there are certain failure causes. And failure causes will lead to some load, to some wear out. And in that way, when we test for reliability, we can say these conditions which are representative in use must be verified by testing. Okay, and now we have seen there are a certain number of standard methods. The initial standard set of standards comes from the US military, and it was designed in the 60s. Yeah. In the 1960s, there was a Vietnam War, and in that war, many equipment was stored in Japan or in the Philippines, for instance. Yeah? And the Americans found out that much of the electronic equipment which was stored, for instance, in Manila, was not working anymore. Yes, it was degraded and it was not functional. And so they investigated why devices had failed, and then they came back to the situation that it was often microelectronics or just electronic devices that had degraded. Finally, the analysis found that there are certain effects like temperature, temperature cycles, temperature shock, which all are more important in, let's say, in the operational phase. We have mechanical shock, which means you often drop it, yes, or you have installed something in a, let's say, in a Jeep, for instance, yes, and it's a bumpy road, and that leads to shocks. And at the same time, we also have vibrations. Then that was not so important in the 60s, power cycling, but later on, when power semiconductors were introduced more and more, it became evident that the self-heating of these semiconductors had an effect on the temperature. Here, the temperature means the environmental temperature. And here in the power cycling, we have temperature plus self-heating by dissipated power, because every semiconductor has a limited efficiency. Maybe in the beginning it was 90%. Now it's going towards 99% in modern power semiconductors, and that means quite a lot of heat is lost and heats up the system. And then that was a problem of Manila, moisture or humidity and climate. That means moisture. Moisture means it's really wet. Humidity means there is water in the air. Yeah, not as water, but as a part of the air, which can be saturated also with water. Then we have chemical media. Okay, when you install devices in some, for instance, mobile equipment, there always will be media. And also what was found out is that for a device, it makes a difference if it's a device that is just tested or if it's a device that was soldered previously before testing. And normally in equipment, especially at that time, one had to assume that every soldered equipment is soldered at least twice. Yeah, that the reason is that often at that time, because electronics were very expensive, we had rework. So when it was found, we soldered the board and it's not working, then analysis finds out we have that device which is defective, and in that way we must exchange it. So it is soldered out and soldered in again, and in that way, and sometimes the second soldering is not done by hand, but again in the machinery. So the equipment is typically soldered twice. And on the other hand, a soldering cycle at that time went to, let's say, 200, 210 degrees centigrade. Now it's going even to 240 degrees centigrade. And that's really, you could say, a birth shock, yeah, for the equipment. And it can lead to a certain pre-damage. And then the subsequent reaction to mechanical shock, for instance, is different. And that's the reason why in these standards, the soldering cycle was introduced. And just to say it, that is something which should always be done in combination with the other tests. Okay, that was military standard. From 1990 on, there were several trends. One of the trends was going away from hermetically sealed devices. So that means ceramic and metal packages to plastic packages. And plastic packages at that time were estimated as much more unreliable than hermetically sealed devices. And the second thing was that from that time on, use of semiconductors became more important in non-military applications than in military applications. Up to the 1980s, at least up to the 70s, the biggest customer of electronics was the military. And only since, let's say, 1995 or so, automotive industry has become important for reliability, as a customer of semiconductors. From the let's say 70s on, of course, more and more microcontrollers became important. Then we had the Apple II microcomputer. Soon after that, we had the IBM PC from, let's say, around 1980 on. And then the PC became important and still is. And only, let's say, for 15 years now, we have smartphones and such things. Okay, so the military became less important. And so the standards had to be transferred to the civil area. And here we have the JEDEC. It's also an mostly based American organization, which published lots of standards. But most of the standards, we can say, was in some way copied or based on the military standards. Yeah, they were already successful. So you could say when you look at military standards and look at JEDEC, there is quite some similarity. Yeah, so I'm also quite sure that people who helped developing military 883 in standardization committees were later on in the JEDEC. And then there is something new. Now the automotive industry became important from 1990s on, mid of 1990s, and they invented something very new, which was the AEC standards. That means Automotive Electronics Council. Initially, that was founded by the big so-called OEMs, that is original equipment manufacturers, and that in automotive industry, that means the companies building cars. Yeah, and then they have suppliers. Tier 1 is so the first level of suppliers, and like Bosch, for instance. Initially, that AEC was carried by the automotive industry. Later on, let's say from 2000 on, automotive industry, somehow they retracted from such standardization. The argument there was reliability is suppliers' business. Yeah, it's not our business anymore. Result was big quality problems around 2000 or so, even with Mercedes cars. And yes, here we have the AEC Q100, which is based is for microelectronics. But again, it's nothing really new. When you look at the AEC Q100, you can say, okay, there is much similarity with JEDEC and also with military standard. Yeah, so in some way they adapted these standards first for civil area and second specifically for automotive area. As I said, in the meantime, the big automotive companies, they withdrew from that standardization committee. Now it's more Bosch and such companies, or what is it in Japan? Okay, and they defined that. Okay, and the testing must fulfill two aspects. One is the environmental conditions, or let's better say the environmental and operational conditions must be represented by the testing. That is important. On the other hand, it also must be sure that the failure modes you stimulate by testing are still the same as they are in the field application. Yeah, so it makes no sense. Maybe you have a special failure mode in the field and you cannot really stimulate it by your testing. Yeah, then you have, yes, some gap in your testing scheme. And on the other hand, it also makes no sense introducing a new failure mode, for instance, by testing under too hard conditions. And that failure mode will not occur in the field. Yeah, that makes also no sense. Yeah. Sometimes the testing in the lab is harder than in the field. The reason is we want to accelerate failure. Yeah. So, and that you can only do by increasing the load and increasing the stress on the device. So that's clear. And in that way, just by stressing more, you can introduce other failure modes. Okay, so we have, of course, many things which are important. One is the interconnections, so the solderings, wire bonds, and so on. Then, for instance, in MEMS or general devices, we have the attachment, how it is attached. That can have an influence, especially in temperature cycles shock. Here again, in the die attachment, we can see it's not only a question of production, but it's also a question of design. Who did not yet attend assembly and packaging or Aufbau-und-Verbindungstechnik? Who was not? Okay, the rest should be, so you know about delta alpha problems. And these we have typically when we cycle and when we do power cycling. Then we can have package defects. The question is, how are they stimulated? And again, it's often by thermal mechanical phenomena. And also here, the soldering cycle is always important because it leads to high stress. Then we have leakage and hermeticity, which is often a result of mechanical effects. Then we have the external leads. So often devices have their legs, which are used to solder it somewhere. A leg is a high aspect ratio structure, and high aspect ratio structures, either something which is unidimensional or two-dimensional, which means it's some sheet light, they are very sensitive against vibration. Yeah, because here we can have large amplitudes, and so such and also because we have that aspect ratio, we typically have relatively low resonant frequencies, and it's resonant frequencies in the range which can occur, for instance, in a car. Yeah. On the other hand, when we have something like a really bulky structure, it also has resonance frequencies, but they are maybe in the 20 kilohertz or 100 kilohertz, and these frequencies typically do not appear as mechanical frequencies. Yeah, so it's more the lower range of frequencies up to 2000 hertz, which is a typical value. And these leads are high aspect ratio structures. On the other hand, leads can oxidize. They are metal structures, often coated with nickel, gold, or with tin, and this can corrode. Then generally, metal parts, corrosion effects. We can also have corrosion effects on the chip metallization if the protection is not perfect. Yes, and here we specifically mentioned high aspect ratio structures, but again, leads are also such structures. Chip cracking is something which is happening often. So you can say often you have either the attachment failing or the chip failing. And what also is often affected is electrical parameters. These testings can also have an influence on the device performance and the functional behavior, and that can be both in a way that it leads to failure, but it can also lead to some fault. Yeah. Imagine you have a differential amplifier, yeah, and now that amplifier is somehow in a temperature field which has a gradient, yeah. So differential means now you have a temperature difference between the two amplifiers. Normally, if the temperature difference is zero, also the output signal will be zero, but just because temperatures are different, both amplifiers behave different. You subtract it, and now you get a signal. That can also be an effect, yeah? So that's more a fault or some characteristic curve is affected, and in that way, electrical parameters can be influenced. And okay, now I already mentioned what testing must fulfill. It must be representative of the operational conditions. All of the field relevant failure modes must be stimulated. The test times must be sufficiently long, but they must not be too long, because normally we want to have the result maybe in a few months, yeah, not longer. And failure data must, in most cases, exhibit sufficient statistical significance. So maybe one failure is not really significant. Okay. Now the JEDEC conditions are, here is an overview of the standards we have. I will not go through that list. What is important, like every standard or family of standards, has some kind of synopsis. Yeah. So here are the general specifications for plastic encapsulated microcircuits for use in rugged applications. So that's a general. And then we have another general aspect, which is a stress test driven qualification of integrated circuits. That means we have a certain strategy in our testing. Another aspect is before we test something, we should have a look at it, yeah, just to have an influence. So if it already looks not well, it makes no sense testing it, for instance. Yeah. Also, there is some preconditioning, like the soldering before you start testing. And then there are several tests. When we look here at the purpose, we can say reliability. That always means we look if there are failures after that time. On the other hand, sometimes we do not really get reliability data. So reliability, to repeat it, means we have a certain test time, and we look how many fail, yeah, over time. N divided by N, and capital N is the number we had initially. So it increases. And at some point we can define a reliability which is 1 minus n divided by n, and over time. And so reliability always means probability and time. On the other hand, for some conditions, we cannot really give it that way. And we rather look what is the strength, yeah? And we say, for instance, we share of a wire bond and specify a certain minimum strength. And then we assume that when it's stronger, it will live longer. That's something which seems to be reasonable and often is true, but not always. Yeah. So as a replacement for reliability test, we cannot perform, or as a preliminary test before reliability test, we test for certain strengths. Yeah. It is similar when we look for vibration. Vibration is typically performed not just on a device, but often on a system like a printed wiring board. So we have structures that can vibrate, and nowadays often vibration is really done as a reliability test, like to build something up, like the Baskin curve, for instance. Yeah, Baskin curve means we have the number of cycles as a function of the stress level or of the G level. Initially, such vibrational tests were different. They were very limited. They went, for instance, from 20 to 2000 hertz and at a certain amplitude. And it was just looked if devices can survive it. Yes. So it was more a strength test than a reliability test. But as vibration has become more and more important, especially in the automotive industry, it is from initially more a strength test, it has been developed more towards a reliability test. Also in vibration, you can say there is very much, let's say, yeah, a chance of the influence of design. Yes, you can say you go in that 20 hertz to 2000 hertz and up and down and up and down for several times, maybe 3 times. And if you have some resonance of your system, then there is a big danger that it is destroyed by resonance. But if there's no resonance, typically you will not have a problem. And in that way, that test initially as a strength test was looking more, do you have any vibration problem here in your system? Okay. And also what we have in the corrosion, there is a strong influence of, yes, what are the 3 factors having influence on corrosion? When do we have corrosion? It's 3 just general conditions. Yeah, more precise, not humidity, but moisture. You have water in a liquid form, and then you can have an electrolyte. Yeah. Corrosion is an electrolytic process. It's not just a chemical process. Yeah. When you throw sugar in water, it's a chemical process of just a more a physical process of when you have corrosion, it's an electrochemical process. And if it's chemical process what will have influence on the speed of that process? What properties define electricity? Voltage, yes, a potential. If you have a potential difference, like in that battery, you have an anode and a cathode, yeah? The cathode is protected when you discharge it, and the anode is dissolved in some way. Okay, it's the same in corrosion. The trick in corrosion is that the surface of the metal in most cases is simultaneously anode and cathode. When you have an electrical potential on that metal part, you shift it more to the anodic side, or you can shift it more, and you increase the rate of corrosion just by the potential. You can reverse the potential, and then you can protect it cathodically. And in that way, we have two factors. One is liquid water. Second is the potential has an influence, but we can also have influence when the external potential is zero. But in electronic devices, some have positive, one have negative potential. So some pins are protected, some are more prone to corrosion. And the third thing is when we have an electrolytic solution, it must be conductive, yeah? And the conduction is a result of ions we have. So that's the three parameters we have in corrosion: water or water film, electrical potential, and ions. Ions make the water a bit more conductive, and ions also have an aggressive effect, yeah? Especially chlorine. They make the water conductive, like when you put sodium chloride into water. But on the other hand, also the chlorine attacks most of the metals, especially something like aluminum or such metals are attacked by chlorine. So in that way, we have a highly accelerated temperature and humidity stress test. So that means we put voltage to the devices. They are in a humid or damp climate, and the ions, normally we assume it's not the ions from the outside, but the ions we built into the electronics. How clean we were in production has influence. So in that way, that gives some background why we test here. Or for instance, cycled temperature humidity bias live test. Bias means voltage on it. Cycled temperature humidity means we have condensation, yes? And then we are really sure we have a water film. And in that way, there's a complete set of tests, but these tests are not just, let's say, selected in a more or less arbitrary way, but they are really based on physical considerations and on considerations of an analysis why something failed. Okay, and yeah, no, I will not go more through the details here. One test which is very important, especially not so much in single devices, but when you build modules, it's temperature cycling. In the end, there is also sometimes standards use different wording. For instance, here we called it temperature shock. That means we go into a chamber, and in that chamber we have a hot area and a cold area. It's like mounting an oven on a fridge, yeah. And then the part is in an elevator, and it's coming from one area through the other, and that machine, it has a strong ventilation here, and in that way there's a very fast exchange of temperature in the devices. So it is called, so that's according to some ISO standard, it's called temperature shock. When you go to JEDEC standards and look at temperature shock, it's and which is used for devices, then it's something different. You have to bath, yes, a hot bath, like a, what do you have, a fondue bath, or so it's a hot oil or something like that. And on the other hand, some solution which is cooled to some minus temperatures, and then the device is just dipped in and taken out and dipped in just by a robot arm or so, and then that is called temperature shock. Yeah, but yes, here let's talk about the ISO standards, and here it means we have a transition time of 10 seconds, but of course, depending on the thermal mass of the devices, it takes a certain time until these have adapted to the new temperature. So if it's a little bigger part, it's not the 10 seconds it changes temperature, but it can be minutes at least. Yeah. So typical times are here 30 minutes dwell and 30 minutes dwell here. You can also go into a slow test, and here that's something like an oven in this most simple version, but it can also be, again, a combination of cooling and heating. And so you can have a temperature ramp up and down with a well-defined slope of temperature change. That is slow temperature cycle, which is more representative, of real environment, you could say. The temperature shock, we must say, it has additional stress compared to the slow temperature cycling. Why is that so? Let's think about that part here. Now I do such a slow temperature cycling. How is, when you look at the temperature distribution in that part, how is it when you cycle slow? Yes, it's uniform, yeah? So even distribution of temperature in that part. Will that lead to stress in a uniform material? No, not. On the other hand, when you dip it, for instance, I dip it in liquid nitrogen, for example, what will happen then? The outside is extremely cool. It will contract, yeah, and that will lead to the fact that inside we have compressive stresses, but the outside layer has tensile stresses, yeah. And that means tensile is often bad. It can crack just as a result of the speed of temperature change, yes. So, and that's the reason why we have different rates of temperature change. Or here we had a cycle that was in one of our projects that was really a slow cycle, which would somehow simulate the operation of a car. So car is increasing in temperature. So normally the complete car is heated up. Maybe it takes a quarter of an hour or so. Yes. And then when you shut it down, you have a high thermal mass. Alone your engine has a weight of 150 or 200 kilos. So that means cooling it down takes time. Yeah? And that would be such a cycle you can go for. And in the end, that's a typical test which you perform on printed wiring board based assemblies. On the other hand, when you have assemblies which are more power cycling, which are more having higher power, you prefer power cycling test. When you do that testing, typically you first do visual inspection. As I said, you look if you already see a problem, you will not test it. Then typically on the device level, you do device-specific functional test. Then you do reliability testing. So that means cycling and other testing. But here we must say, normally what you don't do is just all of the set of testing, but we always take only one of the tests and perform it in that way. For instance, temperature shock or so, or high temperature operation. And then you do again functional testing. And after, in the end, there is a decision, is a qualification goal achieved. Yeah. And the degradation of functional parameters on the device level must be monitored. And other failure criteria can be applied. Of course, the most important failure criterion is when the device is dead, yes, when it's not working anymore. Or sometimes it happens if you measure all combinations of pins, for instance, suddenly you have a short circuit between two pins, which should not be there, or you expect a connection between two pins and you don't have that connection, so you have an open. Of course, all of these are failures, yeah? Dead or open or short, or functional parameters, as we mentioned, but these cannot be put into standards. These are really device dependent, yeah? Every device has other functional parameters that are important. And a third criterion is how does it look? So if it looks like degraded, or if it has cracks on the outside or so, of course, also it is considered as a failure, even if it's still functional and still is within the limits of the functional parameters. So that's important. When is it failed? I once made a consulting for a company, and this company was building the electronics for an anti-brake locking system for motorcycles. And in that anti-brake locking system, you have a pressure sensor which measures the pressure on the braking fluid. Yeah. And that device, it was not in a way that it didn't function at all, yes, but because that pressure sensor had a defect, so it's 0 point shifted, yes, and that meant for instance, the anti-brake locking system, in the end, it would start operating at other conditions you have, yes. So not under the controlled conditions, and in that way it would not function properly, and evidently that led to some accidents. Yeah, and in that way you can say the device didn't fail in a normal sense. You say it's not working anymore just because it gave a wrong value. The complete system lost its basic function. Yeah, and so it's really important to address what the functional parameters are. Again, it's also important when you look at the V model that you know what the influence of a certain defect on the lowest hardware level can be on the system function. Yeah, but that we will see later on how that can be addressed. Today we just talk about more the basic level of devices, and normally to start with something simple, we look at the failure rate. Failure rate is a probability change per time. And failure rate, on the other hand, is the probability of failure per time, but as it is a probability, it's a relative value related to the devices existing at that time. Yes. You have a certain population, you know so many people, you have 1 year, you know so many are born per year, let's say it that way. So you have a birth rate, yeah, per year. On the other hand, you also have a death rate, yeah. So it's the number you have, 1,000,000 die. So you have that death rate of 10 to the power of -3 per year, and that's related to the number you know that is now existing. Which property is it which is related to the number which were, let's say, ever born in your time you regard? That's a density function. Yeah, the density function is related to the number produced. Yeah, and the failure rate is related to the number existing. And now a failure rate, when we do it, we take a certain number of devices. That here is used capital N multiplied with TA, and TA is here the testing time, and that's your testing effort you have. And then over after that testing time, you look how many have failed, and that's a failure rate. And now it is assumed that that the failure rate is constant. Of course, we know that is not true at all, but to keep things simple here, we do it that way, and that's an estimate. That's an estimator. We estimate it just on the basis of data we have it. The estimator for the failure function is just n divided by n. 50% fails, so f of t is 0.5. For small values of n, we need a corrector, but that's not important here. And we can also say for short times, the estimator of the failure function is something like the estimator for the failure rate times the time of testing, or the time we consider here. That is only for relatively short times. And now the question is, when I have a test effort of 1 million sample hours, yeah, 1,000 specimens, 1,000 hours tested, that's 1 million. Now I have one failure here. That, what is the fit number then? How many fit is that? So it's 1,000 fit, yeah? One fit is 1 in 10 to the power of 9, but here we have 1 in 10 to the power of 6, so it's 1,000 fit. Okay, so we have a fit rate based on 1 failure. So that means maybe the part is not so unreliable, but can we rely on that data? The probability that error is that value is not true is quite high. Yes, and so a method was developed by some mathematicians in order to correlate that with another probability, and that's a probability defining the statistical significance or the confidence level we have. And the alpha is the significance level. It is a probability, and that's a probability that your value you give is wrong. On the other hand, there is a complementary value, says, okay, the probability that this value is true, and that's a confidence level. So that's important. Significance level means probability of error, confidence level, probability of being true. And now, let's say in semiconductor industry, people talk about 2 confidence levels. One is 90%, I would say that is reasonable, but they also worked with a confidence level of 60%. And 60%, I used to say it's almost 50-50 chance, yeah? So it can be that side or that side. So let's first talk about 1 minus alpha. It's 90%. That means the significance level or the probability you are wrong is 10%. And now what you can do is, if you want to give a failure rate with a certain confidence, you must somehow do some mathematical operation on your estimator, yeah? And you can imagine it that way. If you give, now we had 1,000 fit, yes? And yeah, you don't really know how the probability is that is true. That's just your estimator. But maybe you want to give us a value where it is more probable that it is true, or better, that it is more probable that your part, your cell, is better than that value. And now if you specify, for instance, 2,000 fit, it is more probable that your parts are better than 2,000, yeah? And when you specify 3,000 fit, it's even more probable that your part is better than 3,000 fit. Yeah, that's the idea of that confidence or significance level. On the other hand, when you are a manufacturer, what would you like to specify? My failure rate is 1,000, 2,000, or 3,000 fit. To make your product look good. Yeah, lower. Yeah, okay. And so you see, on the other hand, if the customer accepts a higher specified value, maybe it's helpful for him to know he can rely more on it. Yes, you want to make a system that is safe, where you want to have a real high reliability of the system. Yeah, and then you talk about the probability that all of the values you used have only a 90% probability of being true. Yeah, then that's not sufficient. So how that K factor, it is K3, and I can also explain it to you why we have that K3 factor. If that is based on the chi-square distribution, and there are several K factors. You can have one K1 to K4, and every KE is for a certain test strategy. That K3 is a test strategy where you have you have always the same number of specimens in your test over the complete time. But what does that mean? If one is failing, you replace it with a new one. On the other hand, we must say these test strategies which we have here are not so important, replacement or not, because generally the number of specimens is quite low. Yes. When you have a higher number, the number of failures is quite low and the numbers of specimens is rather high, then it doesn't make so much difference. So let's take that value here. K3 is 1 divided by 2n. N is the failure number. And then we have the chi-square of, that's a 2-parametric distribution function of 2n plus 1. So if you have only one failure, you put in here 2 times 2, then it's chi-square of 4 and 1 minus alpha, and then 1 minus alpha is, for instance, 0.9. So that value of chi-square time of the chi-square function is 405, let's say roughly 4, and you divide it by 2, so your multiplier is 2. So if you have, based on only one failure, a 90% probability that your failure rate you give is true, then you have to take the estimator and multiply it roughly with 2. Yeah, and in that way you get a failure rate which is related to a certain probability that it's true. And in that way, chi-square function, where do we find it? Of course, we go into Excel. There it is. We have the chi-square and the inverse chi-square function. Here I gave it as a table, so it's more evident. What we can also have is we can even give a certain value of the failure rate with a certain confidence level if we had no failures, how can that be? Going in here, lambda is n divided by n times Ta. So here, lambda would be 0. On the other hand, we go into that formula. 1 divided by 0 is infinity. So we have a problem. How can it be then? The whole idea is we just take it as one formula, then the n is eliminated, and then we just have the value of the chi-square function here. And in that way, we can even give a certain probability of failure with a certain failure rate with a certain confidence level, even if we had 0 failures. Sounds a little strange, but when you look back in the lecture notes where we had failure rates, there were some in the table where it says no failures, and it was just used in that way. So you can say lambda 1 minus alpha is n divided by nTA times 1 to n, and then chi-square. And then we can see the n just eliminates, and so it doesn't hurt that it is 0. And then we can calculate a failure rate for that case. So in fact, it's not based on the failures, but it's based on the chi-square distribution. And of course, we must be sure that the chi-square distribution is valid. Okay, and now that is done with so-called lot testing. So when we purchase a certain amount of semiconductors and we want to have just a ongoing quality control, then we can do, for instance, something like that. We get from the supplier 3 lots, each having, don't know why, it's 77 components. And so that it is 231 devices. And when these are tested, none are allowed. I think the 77 and the 3 lots, it just comes, then we have some nice values for the chi-square distribution, and we have some values which are convenient, but in fact I don't really know how these were defined. But then you can say you can accept the lot you get when you purchase these, and you have three test lots of 77 devices with reliability tests, and no failure occurs. So at least you can sleep better. But of course, that's no proof at all for a certain reliability value. And you are only allowed, yes, or it's only sensible to make that test on the lot testing when you previously had the complete testing of determining failure rates. Yeah, you cannot just do that alone, but that test is based on a preliminary test, which is based on a much larger number of devices, and you were testing. Okay, another analysis is the Weibull analysis. We have already seen in that curve here. Where is, no, it's not here. So I just make a sketch. We have the numbers of failures, and that number of failures, or the f of t, is going up in a certain way. And that here is the EOL. What does that mean, EOL? End of life. Yeah, okay. So here you could say somehow here the wear out begins somewhere here. Okay, and in that way, depending on the beta, we can either say we model a decreasing failure rate, so that's the initial part of the bathtub curve, or we model the wear out. And the wear out is very much important, let's say, to decide how strong a device is against stress factors. And the distribution function we typically use is the Weibull distribution. Weibull was a professor in Sweden, and he first used that distribution function he first used that distribution function for modeling strengths, and later on it was used in order to model lifetimes. Of course, we must also say that distribution function, now it doesn't go down, but it tends to go towards 100% or to 1, yeah? But initially it goes up, and normally we are not interested when our 100% cars failed, but when 10% or so have failed, it's already a significant portion where we can say there is a significant danger here. So, but that's such a S-shaped curve, and that curve was known before. Yes, the chemists also use it because a chemical reaction also, when it has consumed up all of the reactants, then it also goes towards 100%. So that curve is also very much well known. Chemists say it's a Aframi curve. Here in reliability engineering, we say it's a Weibull curve. So Weibull first used it. And it's 1 minus e to the power of t divided by the time constant to the power of beta. When the beta is 1, it is which function? It is an exponential function, yes, and the failure rate is constant. So when we want to define that f of t, if we have only a few failures, we must make a certain correction. The j is here the number of failed ones, so it's or we can also say n. N in the other failure rate consideration, it's more the total number failed. Here is a j, just the index, first failed, second, third, and so on. And so we take j minus 0.3 divided by n plus 0.4. So for the very first failures, we make a certain correction to that f of t value. It's not really important for us, but it's done. And in that way, that f of t curve is determined. What is the meaning of the tau, of the time constant here, or the characteristic value, as we say in Weibull distribution? What is the meaning of that? It is a time, but what time is it? How can we get that? What will be f of t if t is equal to tau? Then, so t then we have f of t is 1 minus e to the power of -1. E is 2.7. 1 divided by 2.7 is roughly 0.37. So f of t is roughly 0.632. I know that because I tell it every year. So that's f of t. So if we have that characteristic change or the time constant, that means we have a change of 63%, or that means 63% have failed. In a normal distribution, how many have failed? 50, yes. So you can generally say, just as a rule of thumb, yeah. Typically, also the time, the mean time to failure, for instance, is maybe 10% lower than the characteristic lifetime you get from the Weibull analysis directly. Yes, so you can say the 50% value, 50% is against 0.63. That's on the probability axis, but on the time axis, you can say, as a rule of thumb, the mean time to failure or the mean cycles to failure is roughly 10% lower than Weibull. In fact, you can compute it more precisely based on the gamma function, but I think we will come to that later on. How can we make a check? We have a S-curve, and first of all, now we get some data. For instance, we tested 100 devices, and we notice one fail at that time, next fail at that time, and so on. So we have failure times, and we have the index j. So we have j from 1 to n, and the time tj. Yeah. How can we get that? So in the end, it will lead to some values on that curve here. But the question is, how can we get these two parameters? Two parameters are the tau and the beta. Now, if you want to have the parameters of a distribution function to be derived from some measured value, what method do you use? Maximum likelihood estimation. You heard about that? It's a special method. You form a maximum likelihood function, and based on that, you can derive the parameters. What you can also do is a regression. And if you have two parameters, you make a linear regression. Yeah. But the Weibull function is not linear. So in order to be able to make a linear regression, you must linearize it. Now let's try that. You have that function, and now you bring that 1 to the other side. And then you say 1 minus f of t is e to the power of minus t divided by tau to beta. So on that right side, 2 unknowns are. To the left side, you know that, yeah, because you have that here, yeah. Okay, now what you can do is take away the minus, and then you invert that. 1 divided by minus 1 minus f of t. You can also say it's 1 divided by r of t. Yeah? Okay. And then when you have an e function, you make a logarithm. That means t divided by tau to the beta is logarithm of 1 divided by 1 minus f of t. But you can also say it's minus logarithm of 1 minus f of t. That's just simple rules. And if you have a function with such an exponent and you want to linearize it, you again take the logarithm. Yeah, my math teacher, he used to say, when you take logarithm twice, you can get anything to a straight line. That's not quite true, we will see, but it helps in making a linear regression. And then you can say logarithm of that term here is just beta times logarithm of time minus beta times logarithm of tau. That's a constant, and that's a constant. And you could also say y is ax plus b, yeah? So that second here is the b, and that here would be the slope. And when you make, when you plot these parameters here against each other, these, so the ln t against logarithm minus logarithm 1 minus f, then if it is a Weibull distribution, you will find it is a straight line. Okay. What's another way? What's another way to find out if you have a certain distribution function? So straight line is something qualitative. So you plot it and then you look, is it a straight line or not? If it's a straight line, it's quite probable that function is valid. On the other hand, sometimes you cannot really distinguish. For instance, if the beta is roughly 3 or so, you can also make a test similarly for Gauss distribution, and you will find out, you will not really know if it's a Weibull or a Gauss distribution, yeah, when the beta is around 3 or so. So in the end, what is a quantitative test to find out if it's a certain distribution function? What do you do then? You do a so-called test for distribution, and there are several tests. Some of you heard maybe Kolmogorov-Smirnov test or chi-square test. And then you subtract the expected values from the real values and look if these are, how these are distributed. And you get a certain test value, and based on that test value, you can estimate how probable it is that you have that function. So that's a proper way. We will not do it because we are doing engineering, not mathematics here. So that was enough of math here. And in that way, we can see the y value is beta x minus beta ln tau. And in that way, we can get the parameters, and one is the slope, and the other is the tau, which we get from the offset of that curve. Sometimes we take a 3-parametric Weibull distribution. Here we take initial, you could say, some kind of lag time before it starts. So for instance, you think that it started here, the process, but in fact, it really didn't start here. And that means both the t and the tau, you subtract that lag time. Of course, in some way, you must, you must estimate that lag time. And because now, of course, it's more complicated. You cannot get that. You cannot get that directly from a regression, because it's not easy to make linear, or you cannot make linearization of that curve here. Also, you should not forget, sometimes that curve is given in a way t divided by t0 just divided by tau. Yeah, but I think that's more convenient here. And but you can say you take the curve, and in your curve you can sometimes see before a certain time nothing happens. You just see that from the onset. You say before, let's say 1000 cycles, there are no failures. So in case you assume it's such a 3-parametric Weibull distribution, so the easiest way is you estimate the T0, and then you subtract it, and you plot your linearized. Then you do the linearization, and then you plot it. And maybe it's not yet a straight line. And then again, you adapt that value in an iterative way, and so you can get to estimate what the T0 is. Of course, the modern way is a little more convenient. You put it into MATLAB or such thing, or mathematical program, and it just makes a multi-dimensional maximum likelihood or regression. But the old way was getting that in an adaptive way. And in fact, it doesn't really matter, because in Weibull curve we are always on a logarithmic scale. And so it makes not really a difference if some value is 1000 or 1050 or so, yeah. Okay, that's a 3-parameter Weibull distribution. So if you do such linearization, of course, you can also give the probabilities here. You see it's non-linear. Somewhere here is a 63%. And in that way, then it should be a linear behavior. Here that shows us how we can make also a strategy in accelerated testing. For instance, you have a design, so that's your starting design, and you would know under non-accelerated conditions, you have a quite long lifetime. For instance, for the 63%, you have 2, 3, 4, 5, 6, 7,000 hours. That's too long for test-based optimization. Yeah. So what you can do is you accelerate your test. So the test time decreases maybe by a factor of 10 or so. And then using accelerated tests, so that means more delta T, for instance, you can optimize your design, and on the basis of the accelerated tests, you can come to a longer lifetime. Yeah. Now you have that longer lifetime after 3 optimizations you did. But in the end, of course, you will again try out if that optimization is really valid in the non-accelerated tests. Yeah. And the optimum would be you start here, you do the optimization with accelerated tests, but in the end, you verify that your optimization is still valid in non-accelerated tests. In that way, you have saved, in that case, at least 2 tests which take a very long time. So again, here, of course, that again takes very long. So probably you will not test until 63% or so, but maybe you just look how the curve is here and expect, okay, the slope is still the same. So you can be relatively sure that it's going here. Sometimes we also have the effect that we have some kind of knee here, so it takes much more time until it increases. That's in some cases where we did a very good optimization. So in the end, that shows us just how we can do also an optimization strategy based on the Weibull curve. Okay, so I would say for today we are finished here, and maybe it was a little mathematical today, but it will not be all of the time. Okay, thanks for your attention. Maybe one remark, you see here in this part of the lecture